Hello everyone, so this is the GCSE Science Trilogy Physics Paper 2 Foundation Tier paper that pupils sat in June 2018, and I'm going to walk through it and go through how I would have tackled it. Now, in the description of this video there is also a link to the blank paper and the Markscheme, and also a collection of revision videos that link specifically to the questions in this paper. So, beginning then with question number 1. Which of these is a scalar quantity? Now you should remember a scalar quantity is a quantity that just has a magnitude or size. A vector quantity has a magnitude and a direction. So we're just looking for one that just has magnitude. So if we start looking at them, velocity is speed with a direction, so it's not that one. Force, where if you're pushing something, you're pushing something in a direction, so it's not that. Distance, well, if you've got a distance, it's not necessarily going in a certain direction, it's just an amount of how much you've travelled. So therefore I would think it would be distance, because displacement, you're talking about whether how far you've moved from one position to another in a certain direction. So all of the other three would be vector quantities. Distance is just an amount, therefore it's a scalar quantity. Question 1.2 then. A woman cycled along a straight, flat road. Figure 1 shows the woman's velocity, how it changed over time. So you've got different parts here, A to B, B to C, C to D. Which part of the graph shows the woman moving at a constant velocity? Well, if it's a constant velocity, so you've got velocity on your y-axis, you've got time on the bottom. If the velocity is going up, that means her speed would be increasing. If it's going down, that means her velocity is decreasing. So a constant velocity is when the line is flat, which is between B and C. Question 1.3 then. Which part of the graph shows the woman stationary? So it's either B to C, C to D, or D to E. Okay, so if I'm going to flick back to the graph now, and we can see the part that she is stationary would be when her speed is 0 at the bottom. So it should be between D and E. Between points A and B, the woman was accelerating. We've said that because we know the line is going up between those 2 points. Use figure 1 to determine the total time for which she was accelerating. So I am going to have to flip back towards the graph. So between A and B, okay, how long was the woman accelerating for? So you guys would use a ruler. If you go down, it should be 5 seconds. So she was accelerating for 5 seconds. Again, use figure 1 to determine her increase in velocity between points A and B. So we go back to the graph. A, she started at 0, and B, she reached 6. So therefore, she's gone from 0 to 6, so therefore her change in velocity is 6. Calculate her acceleration between points A and B, and use the equation acceleration is change in velocity divided by time taken. Well, you've just got both of those two numbers from these two questions that you've just done. So your change in velocity was 6, the time it took was 5. If you divide those together, that gets you 1.2, and it's given you the units, meters per second squared. So you'd get 1 mark for writing out the substitution, 1 mark for getting the correct answer. Question 1.7 then. Estimate how a typical cycling speed of 6 meters per second compares with a typical walking speed. So these are some of your values that you just need to know for different speeds. So walking is generally regarded as being 1.5 meters per second. jogging or running is generally considered to be roughly 3 meters per second. And then cycling is, as it said in the question, 6 meters per second. So when you compare it to cycling, 1.5 times 2 gives you 3, double it again, 3 to 6, so therefore cycling is roughly 4 times faster than walking. Question 2 then, it shows a slinky spring used to model a sound wave. So you've got your slinky spring here, and you've got 3 labels that you have to label on. Okay, now this is a particular type of wave where you've got areas where the spring is closer together and where it is further apart. The areas where are close together we call areas of compression, because if you are compressing something, they get closer together. And when they get far apart, it's called rarefaction. Okay, compression and rarefaction. Now, the distance between one wave and another wave is called the wavelength. So those would be your 3 marks using the words from the box below. What type of wave is a sound wave? Well, what we've got here is an example of a longitudinal wave. The slinky spring, where it's being compressed and rarefacted, is a longitudinal wave. A transverse wave is when the wave looks like an S-shaped on its side. Okay, and electromagnetic waves are types, or is a type of transverse wave. So sound waves are longitudinal. Figure 3 shows 2 students measuring the speed of sound in air. One student bangs the bricks together. The sound is produced and it's reflected from the wall and travels back to the students. Determine or describe how they could determine the speed of sound. So, they've got the wall, they've got the bricks, they've got a stopwatch. So what could they do? Well, the first thing they need to do is they've got to know their distance between themselves and the wall. So, measure distance. Okay, they could use it using, keep it simple, a tape measure. Okay, then, once they've got their distance, they need to then get the time. So they can bang the bricks together, and then they're going to time how long it takes to hear the echo. So then you've got distance and time. But what you've got to remember is that actually you've got to double the distance, because the sound has to go all the way to the wall and then it's got to come all the way back. So double the distance, because the sound is an echo. And point number 4, then calculate speed, which is done by distance over time. So speed is distance divided by time. And then, so that would get you the 4 marks. But other things you can do is obviously repeat, remove anomalies, and then calculate a mean. So those are some other parts you could add on as well. Okay, so moving on to question 3 then. Figure 4 shows a man doing 2 stages of a pull-up. In both diagrams, the man is stationary. Complete the sentence. Choose the answer from a box to do this. In stage 1, the downwards force of the man on the bar is blank the upwards force of the bar on the man. So effectively what it's saying, if a man's hanging from the bar and he's got a certain amount of weight pulling it down, how much force is the bar countering the weight that is being pulled down. Now it's told us in the question that the man is stationary. Okay, so therefore if he's stationary, he's not moving, the forces must be balanced. So because it is balanced, the forces then have to be equal. So question 3.2. The man had a mass of 85 kilograms and the gravitational field strength on Earth is 9.8 Newton kilograms. Calculate the weight of the man, and it's told you weight equals mass times gravitational field strength. So the mass is 85, gravitational field strength is 9.8. What you can do is then times those together, and that gives you 833 newtons. 1 mark for substituting, 1 mark for getting to your final answer. Question 3.3. The man raises his body a vertical distance of 0.63 metres to go from stage 1 to stage 2. Calculate the work done by the man. Use your answer to question 3.2 and use the equation work done equals force times the distance. So our distance from the question that he's pulled himself up is 0.63 metres. But what is our force? Well, that would be our answer to 3.2, the weight that is being pulled down. So it would be 833 times by 0.63, therefore giving us 525 joules of energy. Question 3.4. The man was not moving at stage 2. How much work is done by the man at stage 2? So if he's not moving and he's just hanging there, he's not moving any distance, and therefore because his distance is 0, okay, he is therefore doing no work, because anything times by 0 is 0. So the work done would be 0 joules. It's only 1 mark, so that is why it's such a simple answer. Question 3.5 then. A woman uses the bar to do a pull-up. The woman has a mass of 62 kilograms. She accelerates 11 meters per second squared. Calculate the force on the woman. It's told you the equation. Force is mass times acceleration. So it would be 62 times by 11, which gives you 682 newtons. So again, 1 mark for substituting, 1 mark for calculating the correct answer. Question 4 then. Figure 5 shows the types of waves within the electromagnetic spectrum. So we know the question is about the electromagnetic spectrum. Some of the types of waves are represented by letters. Okay, so we've got gamma, starting this side, then S, then R, then visible, then Q, then microwave, then P. Now, before I even begin, if I know my electromagnetic spectrum, I could just fill it in using what I know. So I should know that gamma rays is when you've got really, really high frequency waves, okay, and a small wavelength, and then slowly they get longer and longer, going down to a lower frequency. So gamma rays are high frequency, low wavelength or short wavelength. And then over here we have a low frequency and a large or a long wavelength. So the order then, and there's loads of different mnemonics that you can use to remember it. Use whatever one works for you. So gamma, S would be X-ray, then R would be ultraviolet, then visible light, which we can see, then we've got infrared, then we've got microwaves, then we've got radio waves. So that is the electromagnetic spectrum. Which letter on the position Which letter shows the position of ultraviolet radiation within the electromagnetic spectrum? Well, I've already done that, so it would be R. Question 4.2 then. A special lamp can produce UV radiation. Which two statements describe the electromagnetic waves emitted by a UV lamp? They have higher frequency than X-rays. Well, if we look at this and our diagram, actually X-rays have a higher frequency, ultraviolet doesn't, so it can't be that. They have the same speed as visible light. Well, in the electromagnetic spectrum, all of these waves do have the same speed. Their frequency and their wavelength change, but they all travel at the same speed. Okay, so it is the second one. They have longer wavelengths than microwaves. Well, if we look at our diagram again, okay, actually microwaves have longer wavelengths, so that's not correct. They have a lower frequency than gamma rays. Well, actually, yep, that one looks correct because gamma, it has the highest frequency, so therefore UV must have the lower frequency. Okay, and therefore the last one, they have a greater wave speed than radio waves. Well, that's not correct because they all travel at the same speed. Question 4.3 then. UV radiation is used to treat vitamin D deficiency. People should not use a UV lamp for long periods of time. State 2 risks of high exposure to high levels of UV. So this is the key dangers of ultraviolet light, and this is what it can cause. The key major one is skin cancer. Whilst UV isn't really dangerous enough to get into our internal organs, it can cause cancer of the skin. It can also cause eye damage or aging of the skin. You would get 1 mark if you said sunburn, because it does create sunburn, but the key risk is that it creates skin cancer. Ionizing radiation is used for some medical imaging. Name the 2 types of electromagnetic waves that are used in medical imaging. Okay, so we've actually got some options here, because obviously the obvious one is X-rays are used for medical imaging, but you can also use gamma rays and ultraviolet. Okay, so X-rays is the obvious one, but you can use these other 2 because they are also high frequency, which can then get into your body and see different parts of it. Question number 5 then. Figure 6 shows a man using a resistant band when exercising. The resistance band behaves elastically. Question 5.1. What happens to the store of the elastic potential energy of a resistant band when it is stretched? So as he's pulling it apart, what happens to the elastic energy store of elastic potential energy? Well, it's going to increase because he's putting energy into it from his muscles to stretch it apart. What happens to the resistance of the band as it is released? Okay, so what's going to happen to it? Well, initially it will return to its original shape. And it's a 2 mark, so we've got to say why it's returned to its original shape, because there is an elastic force. Okay, so the elastic returns it to its original shape. Question 5.3 then. Figure 7 shows how the extension of the resistance band changes as the force applied changes. Describe the trend shown in the graph. So we've got this line here and we just need to describe. Describe means say the pattern that's in front of you. Now there's no numbers to this, it's just a sketch graph and we've got 2 marks. So we've got to say what happens. So I would normally then break it into stages. So you've got stage 1, then you've got stage 2, and then you could potentially say about stage 3 as it starts to level off here. So at stage 1, okay, initially, when there is a little force, the band does not stretch. At stage number 2, when it is more force is added, then as more force is added, the extension increases. And we can then say, because it isn't going up in a straight line, okay, it's not a directly proportional relationship, it's not a linear relationship. If it goes up in a straight line, we can describe it as linear, but this, because it's a curve, is a non-linear relationship. So next part then, figure 8 shows a chest expander. Sketch a graph on figure 9 to show how the extension of a spring in the chest expander changes as the force applied changes. So what's going to happen to the extension of it as the force goes up? What's going to happen to our extension? Now they haven't actually given us too much information about this, so we can only use kind of common sense logic, which is starting from the origin, which is 0, if your forces go up, your extension is going to go up. So we can describe this as a linear relationship. Question 5.5 then. When a force is applied to a spring, the spring extends by 7.5 centimetres. Write down the equation that links extension, force and spring constant. Well, the equation you should know is force equals spring constant times by extension. Calculate the force applied to the spring. The spring has a spring constant of 1,600 Newton meters. Use the equation from above. Okay, so we need to calculate the force, which is our unknown. Our spring constant, we've been told, is 1,600, and the distance is 7.5 centimetres. Now, because it is in centimetres, we would need to convert it into metres. And we can get an idea that we might need to do something like that because it's worth 3 marks. If it was just a simple times them together calculation question, it would probably only be worth 2 marks. So we need to convert centimetres into metres. So you could divide that by 100. So that gives you 0.075 metres. Times them together gives you 120 newtons. So that would be your final answer. 1 mark for converting, 1 mark for substituting them both in and timesing them, 1 mark for getting to your final answer. Question 6 then. Figure 10 shows a lorry. The brakes of the lorry are in a poor condition. What effect will the condition of the brakes have on the thinking distance and the braking distance of the lorry? So the thinking distance, this is all about stopping distances. The total stopping distance of an object is equal to the thinking distance plus the braking distance. Now the thinking distance is all to do with the actual driver, okay, and his reaction speed. It's the time it takes for him to see the hazard and actually apply the brakes, whereas the braking distance is actually on about the condition of the brakes and the tyres and the road surface. Okay, so would the condition of the brakes, what effect would it have on the thinking distance? Well, the brakes don't affect how well the driver's thinking, so it would have no effect. The thinking distance would stay the same. Okay, no effect. But the braking distance, if they are in poor condition, it would increase the braking distance. And make it longer for the object, for the vehicle to stop. Question 6.2 then. Using a handheld mobile phone whilst driving is illegal in the UK. Table 1 shows the effect of using a mobile phone on thinking distance. So you've got, when you're not using a mobile, it's 19 metres. If you're using a hands-free kit, it's 23 metres. If you're using a handheld mobile phone, it goes up to 27 metres. Explain why driving using a handheld mobile is more dangerous than using a mobile with a hands-free kit. Use the data from table 1. Well, this is quite simple and quite obvious. If you're using a handheld device, it increases the thinking distance because your reaction time is increased. Because you are distracted on something else, that is going to decrease your reaction time and therefore increase the distance it takes you to stop. Okay, and then because it's 4 marks, we could also quote some data. So handheld takes 4 meters extra to stop. Okay, so the overall stopping distance increases. Okay, so you would have got 2 marks for this top part. So it's saying, as the handheld device, it increases the thinking distance because your reaction time is increased. 1 mark for actually quoting the data, saying it's 4 meters extra, and therefore saying it affects the overall stopping distance. Question number 7 then. A student investigated acceleration using gliders, an air track and light gates. The air track reduces friction between the glider and the track to 0. So effectively, the glider doesn't actually have any contact with the track because you've got air being pushed up on it, and that makes all the friction disappear. So figure 11 shows the apparatus. So you've got the glider and the card here. You've got the light gates, the start one and the finish one. You've got the string, be it pulling it along. You've got a bench pulley and you've got a mass holder. The glider was released from rest and moved along the track. The mass holder hit the ground before the card passed through the second light gate. So when the mass pulled it down and then pulled the card along, it had already hit the ground before the card had actually managed to go through the second light gate. What 2 statements describe the effect this would have on the glider? Okay, so its acceleration would decrease to 0. Well, if it's not being pulled down anymore, because the mass holder, the thing that's giving it the acceleration, is already on the ground, it would decrease to 0 because there wouldn't be anything else pulling it down. Its acceleration wouldn't increase because there's no more force pulling it down. The resultant force on it would decrease to 0. Well, that is true because you've got nothing else pulling it down, so therefore the overall force would go back down to 0. The resultant force definitely wouldn't increase, and its speed would definitely not increase. So it would be the first and the third statements. Question 7.2 then. The mass holder should not hit the ground before the card passes through the second light gate. Suggest one way the student could stop this happening. So what he could do is quite simply, if he's having problems with it hitting the ground, is use a taller table. Or you could, so it's just suggest one way, so any logical answer that would solve it would get the mark. The other way would just be to shorten the distance between the light gates. So next part of the question then. The student increased the resultant force acting on the glider by adding more masses to the holder. So when it falls down, it's going to pull the trolley more. She calculated the acceleration of the glider for each resultant force. Each test was done 3 times. Table 2 shows the results. The student made 2 results in calculating 2 mistakes in the mean acceleration column. Identify the mistakes the student made. Suggest how each mistake could be created. Okay, or sorry, could be corrected. So you can see initially, just by looking at the means, what's different about all of them. Well, 1 hasn't been rounded to 1 decimal place, okay, or 2 significant figures. So mistake number 1, because results table should always be consistent, mistake 1 is 0.2 newtons acceleration has not been given to 2 significant figures. Correction, calculate it to 2 significant figures, and in this situation, if it is 2 significant figures, the 6 is higher than a 5, so it would just be 1.3. Okay, then if we have a look at the other mistakes on it, so 2.6, 2.5, 2.6, that seems right. 3.8, 3.8, 3.9, there's nothing wrong there. 5.1, 5.1, 5.1, that's all correct. 6.4, 6.4, 7.2. Well, potentially these two are very similar, but this one I would say is an anomaly because it's significantly different compared to the other two. So, mistake, she has included 7.2 in her calculation. So the correction would be to remove the anomaly from the mean. So therefore, it would go back to being 6.4 instead of 6.7. Question 7.4, write a conclusion for this investigation, use data in table 2. So it's only 1 mark. So I'll flick back to the table and we can have a quick look what's happening. So as the force is going up, what's happening to the acceleration? Well, is also increasing. So as the force increases, the acceleration increases. Okay, and you could also say, if we look directly at the numbers, it's going up roughly the same amount each time. So you could say it is a directly proportional relationship. But because it's only a 1 mark question, just by stating the simple pattern, that's enough. Question 7.5 then. The student used a constant resultant force to accelerate the glider. The student changed the mass of the glider and calculated the new acceleration. She repeated this for different masses of glider, keeping the resultant force the same. So now she's not changing the force, she's changing how heavy her glider is. So it's getting heavier and heavier, and you can see what's happening to the acceleration. Plot the results on figure 12, draw a line of best fit. So 0.6, you go to 3.5, so it's quite a simple scale they've given us. 0.08, okay, is 2.6, so 2.5, 2.6. 0.10 is 2.0. 0.12 is 1.7. And 0.14 is 1.4. Okay, now actually looking at this, whilst I would have maybe expected a straight line, what we've actually got is a bit of a curve. So you would get your line, and because your line of best fit is showing a curve, you would draw a curved line of best fit. In science, remember, line of best fit can be a straight line or a curve. Generally, in your maths papers, the line of best fit is always a straight line. Remember, in science, we can have it as a curve. 7.6 then, describe the relationship between mass and acceleration. Well, it's the opposite of what's happening before. As mass increases, acceleration decreases. Or instead of saying it's directly proportional, we can say it is inversely proportional, because as one goes up, the other goes down. Question 8 then. A magnet produces a magnetic field. Which diagram shows the magnetic field pattern around a bar magnet? So we should know that a magnet, its magnetic field lines come out of the north and then it loops back round to south. It always goes north to south. So it should be the first one here. Question 8.2. Figure 13 shows 3 metal blocks. The blocks are not labelled. One is a permanent magnet, one is iron, one is aluminium. Describe how another permanent magnet can be used to identify the 3 blocks. So we've got one is potentially iron, one is potentially aluminium, one is another magnet, and then we've got another bar magnet for us to use to test them. What would happen, basically how can we use this other bar magnet, and what would we see to test each of these different metal blocks? What would happen? Well, if we brought iron and a bar magnet, remember iron is one of the 3 magnetic materials, so iron, it would attract towards the bar magnet. If you had aluminium and a bar magnet, now aluminium is not a magnetic material, so nothing would happen. You would get no attraction. And then the last one is the other, so if you had a bar magnet and another bar magnet, well, what would actually happen? Well, you could get attraction if you brought a north pole and a south pole together, but you could also get repulsion if you brought 2 north sides together or 2 south sides together. So that's the difference. Iron, where you would get attraction. Aluminium, nothing would happen. If it was a bar magnet, you could get attraction or repulsion. If it's a magnetic material, you just get attraction. If it is another magnet, you can get attraction or repulsion. Right, last question then on this paper. Figure 14 shows a toy crane. The toy crane uses an electromagnet to pick up and move the blocks. Explain how this electromagnet is able to pick up and move the blocks, and we've got 6 marks. So we should know an electromagnet is a coil of wire and a current that is flowing through it with an iron core. And that's what we've got here. We've got a power supply, we've got a wire, it's going round the electromagnet, around the iron core, and when the current is flowing, that will generate a magnetic field. So point number one, how can this electromagnet be used? What needs to happen? Well, they've given us, on the diagram, a label of a switch, so we need to talk about the switch. Stage number one, student presses the switch, which allows current to flow. Then that current is going to go round and power the electromagnet. The current allows the electromagnet to generate a magnetic field. What would then happen with the blocks made from a magnetic material? Well, they would be attracted to it. The blocks are attracted to the electromagnet. Number four, the student can then move the crane. Number five, now when he's moved the crane, and therefore he's moved the blocks, to turn off the electromagnet, he can press the switch again. This turns off the magnetic field. The attraction will stop. And the blocks will fall down. So effectively, this question is just asking us to demonstrate that we know what an electromagnet is and how it works. Right, so that's the end of this paper then. What you, if you need to, the exam paper and the Markscheme are linked in the description of this paper, but you can go through it yourself. And also there are a collection of revision videos that link directly to this paper. I hope it was useful.